well. But y'all just, you okay, bub? Y'all just tell me if I'm moving too fast. Okay, for an endothermic reaction, is the total enthalpy, and actually I'm going to turn my screen sideways. I think y'all can see this better. Is the total enthalpy of the reactants greater or less than the total enthalpy of the products? So what do y'all think for this one? So endothermic, first off, we've got a positive delta H, and we know delta H equals the sum of the enthalpy of the reactants minus the sum of the enthalpy of the products. So to get a positive number over here, you need to think enthalpy of the reactants or enthalpy of the products, which number is bigger? Yeah, think Abby Mal, the enthalpy of the reactants. This has to be a larger number, okay? Enthalpy of the reactants has to be larger than enthalpy of the products to get a positive number. That's like saying 10 minus 5. That'll give you a positive number versus 5 minus 10. That would give you a negative number, okay? So here, enthalpy of the reactants is larger, and overall that means the reaction is absorbing heat, absorbing energy, okay? And that means your products says reactants. Oh, well, we just answered the question. I just answered it. I didn't realize I just answered it. Total enthalpy of the reactants is going to be greater, okay? Because it's just a larger number. So it'll be greater than total enthalpy of the products. Sorry, I thought I was going to answer whether the potential energy is greater or less. So does that mean, let's actually answer that kind of question. If you have products here, are they going to be more or less stable? Endothermic reaction, would your products be more or less stable? I actually don't have this typed on here, but I think it's a very fair question. We've talked about stuff like this. If you're absorbing energy overall, if you're absorbing more than you're releasing, are your products more or less stable? They're less stable. Jenna typed that in the chat. If you're absorbing energy overall, then you have products with higher amounts of energy, okay? And if you're exothermic and you're giving off energy, meaning the enthalpy of the products is greater, more energy is released than you're absorbing, then your products are more stable, okay? So for endothermic reactions, we'll just make a note here. Products are less stable, okay? U-A-B-L-E. Excuse me, I might not be done. One more, okay. At school, they're teaching my daughter how to sneeze into her elbow. And so I said, Finn, how do you sneeze into your elbow? And she goes, achoo. I said, you're close. Not quite there. All right, estimate, next question, the delta H in kcal per mole for the reaction of hydrogen and oxygen to form water. And darn, I realize we'll have to jump over to another lecture to grab the bond dissociation energy table. I don't have it here, but estimate delta H. So we're literally going to use this equation now and calculate a delta H. But first, anytime you're asked to calculate delta H, you have to have a balanced chemical reaction, and you need to draw the simple Lewis structures for the reactants and products. So go ahead and try that. I'm going to write it out as you write it out. We'll see if we get the same thing. We're doing hydrogen and oxygen. We're going to form water. So it should be, remember, we got diatomics here. Okay, there we go. Hydrogen and oxygen form water. And are we balanced? We're not. So we need a 2 in front of the water and a 2 in front of hydrogen. Now we should be balanced. 4 hydrogens each side, 2 oxygens each side. Okay, now we're going to calculate enthalpy of the reactants and enthalpy of the products. We're going to subtract the 2. So enthalpy of the reactants. Wait, I need to draw Lewis structures, don't I? Lewis structure for hydrogen is just a single bond between 2 hydrogen atoms. And remember, we have a coefficient of 2. So we'll multiply that bond dissociation energy by 2. And in fact, let me switch over to the table real quick and find what that bond dissociation energy is. Okay, I need to go way, way up. Close your eyes. I'm gonna scroll. It's way up here. Keep going. Almost there. Did we get there? Here it is. Okay. Hydrogen single bond is right there, 103. And I don't think I said in the problem to do kcal or kilojoules, so we'll just do kcals here. So 103, and now let's go back over to our slide. We'll plug that in. So we're going to do 2 times 103. Oh, I did say in kcal. Kcal per mole. Plus, we're going to add to that the bond dissociation energy for oxygen double bond. And we just have one, coefficient of 1 here. So switch back over to the table. Oxygen double bond is right here, 119 kcal per mole. Pencil's not writing. Pencil, surely it's not about to die. There it goes. All right, that's everything on the reactant side. Now let's add the product side to, or sorry, not add, subtract. Subtract the product side. And our Lewis structure for water is this right here. In one molecule, we have 2 oxygen hydrogen single bonds, and we have 2 molecules. So multiply that times 2 gives you a total of 4 oxygen hydrogen single bonds. So we just need to go find the bond dissociation energy for the oxygen hydrogen single bond. Here it is right here, 112. And we'll do 4 times 112 kcal per mole. And that's it for the product side. So can anybody tell me this right here is 206 plus 119? That's 3, is that 325? Kcal? I could be wrong. Sometimes I am when I just do it in my head. 4 times 112 should be 448. And total, Jenna said she got negative 123. So what y'all got? Double check us. Okay. And so this would definitely be exothermic. This question's not on here, but it's exothermic. And would we consider heat a reactant or a product? It's exothermic. Heat is a product. So we would write in, you could write in the word heat or energy or 123 kcal on the product side. All right, there's that one. One more of these, and then we'll move on to something else. Acetylene. Okay, this, I like this problem. This is actually, I believe, from your textbook, because this structure right here is real interesting and people will misdraw it. So try to draw C2H2. It's the fuel used in welding torches. And we're going to write a balanced chemical reaction for the combustion of acetylene with oxygen, and our products are going to be carbon dioxide and water. Okay, carbon dioxide or water are the products, and then you have C2H2, oxygen, it said, was our other reactant, and we're going to get CO2 and water, and we also have to balance it. So we have 2 carbons on the reactant side. We need 2 on the product side. So I'm going to put a 2 in front of CO2. And then what else can we do? We've got 2 hydrogens on both sides. And now we have number of oxygens on the product side. We've got 4 total. No, we don't have 4. We have 5 total. 5. So we've got 4 from CO2 and 1 from water. So here's the deal, we can't balance even and odd numbers. We've got 5, that's an odd number on the product side. So when that happens, does anybody know what you should do to balance it? Abby, if you're saying it, we can't hear you. There's a quick fix. It's a little trick. I don't know if it's a trick, but it's the easiest way to fix things. Double the number of your coefficients. So double this first one right here. which means we'll do oxygen last because it's by itself. I don't know if you guys remember anything by itself. Always do that one last. So then we'll double this one, and then we'll double waters. Now, how many oxygen do we have? 4 times 2 right here, that's 8, plus 2 more makes 10 oxygens on the product side. And now we can balance it with a 5 on the reactant side. Okay, so that's balance. Now we're going to estimate delta H. So we need the Lewis structure. So I'm going to draw the Lewis structure for C2H2. Anybody know what I should draw? C2H2, our carbons definitely are bonded together, and each one gets a hydrogen. But we can't stop here because those carbons triple bond the carbons, Jenna. That's the key. That's what people you will usually miss here. Now the carbons both have 4 bonds. Then we already know oxygen looks like this. This problem is also interesting because we have CO2 here. And if you remember, when we go find the bond dissociation energy for CO2, there's going to be an asterisk. We're going to have to grab the numbers beneath the table, not in the table, because CO2 is unique. I'll point that out when we get there. But here's our structure for CO2. And then water, again, we just drew water earlier. All right. So enthalpy of the reactants is going to be, keep in mind the coefficients. Do not forget those. So in 1 molecule of C2H2, acetylene, we have 2 carbon-hydrogen single bonds, but we have 2 of these molecules. So total, that is 4 carbon-hydrogen single bonds. So I'm going to do 4 times my number for the carbon-hydrogen single bond. If y'all can't hear me, I'm sorry. I'm going to talk louder. So what is that number? Carbon-hydrogen single bond is right up here, first one, 99 kcal per mole. I don't know why my pencil is glitching on me every time I go back. 99, there it goes. And in 1 molecule of C2H2, we have a carbon-carbon triple bond, but remember we have 2 molecules. So we're going to do plus 2 times the carbon-carbon triple bond value. And on the table, what is that? Carbon-carbon single bond is right here. We don't want that. We don't want a carbon-carbon double bond. We want this one right here, carbon-carbon triple bond. 201, I wrote over it, 201 kcal per mole. Oh, y'all should stop me. Look what I said. I said do it in kilojoules per mole. We've been pulling the wrong numbers. So that's a quick fix. We just need the 413 and 839. 413 and 839. We've not been doing things in kilojoules per mole. We must have been doing them in kilocalories. So 413 and 839. And then we're still not done with the reactant side. And we have that oxygen double bond. And we got, look at that, 5 of these. So we're gonna do plus 5 times the value for the oxygen double bond, which I think was just on the previous slide because we had oxygen. So we're just, oh, that's kcals though. We gotta get it kilojoules. What was it in kilojoules? Oxygen double bond kilojoules is the 498. 498. 4. So times 498. All right, that's everything for the reactant side, okay? So this will trip people up for many reasons if they're not careful. And then minus on the product side, we've got carbon-oxygen double bond. And in 1 molecule of CO2, we've got 2 carbon-oxygen double bonds, but we have 4 of those molecules. So that means total, the number of carbon-oxygen double bonds is 8. 8 times, and we need the number in kilojoules. So carbon oxygen double bond in kilojoules, and the asterisk is there telling us to go to the bottom of the table. We want this value right here, the 1 in kilojoules for a CO2 molecule. So 799. Dude, I'm trying to teach. Can you keep it down over there? All right. Lastly, we have the oxygen hydrogen single bond again. And the value we want for that in kilojoules is the 467. So plus, and how many? We should have 4 total. 4 times 467, and that's kilojoules. And how we got 4 is we got 2 of these molecules. Each molecule has 2 separate single bonds. So that was 4 total. All right, that's a lot. Somebody want to throw all that in the calculator for us while I put a passy? You want one of these? Anybody, just type it in or shout it out when you get it. It's a lot to add up. And you can, if you want to tell us separately the entropy of the reactants and the entropy of the products, like total, what was the sum of that and the sum of this one? I want it. Please take it. So, okay, Jenna got negative 2,440, and so did Abby. And they got that by doing the 5,820 kilojoules per mole minus, on the product side, it was 8,260. And therefore, we got overall negative 2,440 kilojoules per mole. Any questions on those? I feel like we have practiced and practiced and practiced these a ton. So I hope y'all are comfortable with them. We'll for sure have a problem like this on the exam. All right, next problem. I really like this problem. It says, as we exercise, our bodies metabolize glucose. C6H12O6 is glucose with oxygen, and it converts it to CO2 and water, and that's how we get energy for physical activity. Write a balanced chemical equation for the metabolism of glucose. Okay. It's going to look a whole lot like a combustion reaction, but we're just going to have C6H12O6 plus oxygen, and we're going to get CO2 and water. You getting angry, or are you just talking? It's like you know when we're going to have a review session. You just are very conversational. All right, how do we balance this? Let's try just doing the carbons first. We'll put a 6 in front of CO2. 6. Oxygens now, how many total is that? On the product side, it looks like 6 times 2 is 12 from CO2, plus 6 more is 18. And so we need 18 oxygens on the reactant side. So I think if we put a 6 right here, that would give us 12 plus 6 more here would be 18. 18 and 18. So we should be balanced with a 1, a 6, a 6, and a 6. All right, now question 2 says each mole of glucose produces, keyword here, produces 678 kcal of energy. What is the sign of delta H for this equation? So if overall we're producing energy, is delta H positive or negative? Negative. So delta H is negative. And that's it for that question. So exothermic. But we're continuing the problem on the next page. An individual jogging at 5 miles per hour, which sounds slow, but it's actually not slow. I guess it's relative to every person. An individual jogging at 5 miles per hour for 30 minutes would burn 272 kcal of energy. How many moles of glucose would need to be metabolized to generate this amount of energy in the body? Okay, so 272 kcal. What we're going to do is we're going to use the relationship that we're going to pull from parts 1 and 2. Actually, right here is the relationship. Each mole of glucose produces 678 kcal of energy. So 1 mole of glucose, I'm just going to say capital G glucose. We're going to relate that to 678 kcal of energy. So we're going to now that we have this relationship, remember, you can always relate any reactant or product using the coefficients in the balanced chemical reaction to the delta H. And we're going to use that relationship. We want to cancel kcals because it's asking how many moles of glucose. So we're going to convert to moles of glucose. So for every 678 kcal, that is related to 1 mole of glucose. So then we would just cancel kcal. Seriously, dude? So then this is just a one-step conversion problem. These problems really trip people up, but it is just one step here. Any questions on that one? What'd y'all get? 272 divided by 678. .401 moles of glucose. Okay, so to create that much energy in your body, if your body needs that much energy, or you're going to burn that much, you want to replace it, you need to produce or consume almost half a mole of glucose. Well, how much is that in practical terms? I used to have this problem, say a Lara bar. Anybody like Lara bars? There's all kinds of energy bars out there, and some of them are really expensive. The healthier they are, typically the more expensive they are. But an energy bar contains, and this is true, guys, 20 grams of glucose in 1 bar. How many energy bars would need to be consumed to generate the same amount of energy in question 3, which is how much? 272 kcals. So all we're going to do is we know we're gonna actually, how do we go about this? We need a relationship between kcals, this amount of kcals, and glucose, and we derive that. We actually derive that with our answer. 272 kcals is related to, we would get that amount of energy from 0.401 moles of glucose. That's what you just did in the previous problem. So we can use this amount of kcals, but we want to know how many grams of glucose. All right, actually an energy, we don't know how many energy bars. That's what the question is for. And here's a relationship as well in this problem. 1 energy bar is this many grams of glucose. So we can write that over here. So we're going to need this relationship, 272 kcal. You can actually, you can start with this relationship if you want to, or you can use the relationship from up here as well. That would equally work. If you were like, I don't know where to start with this problem, you could start either place. 1 mole is related to this amount of kcal of energy. or you could start right here. We know this equals 0.401 moles of glucose. And we know that 1 energy bar is equal to 20 grams of glucose. Okay. So how many energy bars would we need to eat? Well, we can shortcut this problem if we do start with this relationship up here. We can shortcut this problem. So we know that we're trying to generate 272 kcals of energy in our body. And we will do that if we consume 0.4 moles of glucose. Okay. So we really just need to know how many grams of glucose is that, and then use this relationship to convert from grams of glucose to energy bars. You tracking with me so far? So here's what we can do. We can actually, instead of starting, oh Lord, he's literally spitting up like almost all over me. Okay, we'll just start. We know this amount of energy, which is the amount of energy we're trying to run with, is related to this many moles of glucose. So we're just going to start with this many moles of glucose because those are equal. Those are related. So if we have 0.401 moles of glucose, let's convert that ultimately to energy bars. We want to cancel moles of glucose and convert to grams of glucose so that we can then take grams of glucose and convert to numbers of energy bars. So how do you go from moles of glucose to grams of glucose? That is molar mass, and I don't give it to you in the problem. If you Google it, it should be 180.156 grams per mole. Okay. So if I ask you this on an exam or something like that, I would give you the molar mass of glucose to complete it. So we know for every 1 mole of glucose, that is 180.156 grams. Now we can say we know 20 grams is 1 energy bar. So cancel grams of glucose and convert to energy bars. So ultimately what you have over here is moles will cancel, grams of glucose will cancel, and then we'll figure out how many energy bars we would need to generate 0.4 moles, which is equal to 272 kcals of energy. So you do 0.401 times 180 divided by 20, and Abby said she got 3.6, so about 3.5 energy bars. But who's going to stop at 0.6, right? We're just going to eat the whole thing. I don't know. I've never eaten 4 energy bars in one sitting. Now, if it was like brownies or cookies, I'm totally down. Okay. Any questions on how we did that? That was kind of a unique problem. It was a different style word problem, but you can see we did the same kind of stuff to answer it that we've been doing all of chapter 6 and chapter 7. All right, let's do this next one. Predict the sign of delta S. So just say whether it's positive or negative for each of these. So I want y'all to take a second, look at these 3 relationships, and then we'll talk about, is delta S positive or negative as you go from reactants to products. Is it positive or negative? Oops, sorry. Now, on number 3, we actually really haven't had one with something that's aqueous. You're going to really treat that like it's liquid, right? Things that are aqueous are dissolved in a solution. So it's pretty comparable to something that's liquid. So Jenna put her answers on. She said she got Delta S is negative for number 1. Let's see. We've got a solid and a gas, 1 mole of gas, making 2 moles of solid. So 2 moles of solid plus we have a gas making one thing. So it definitely looks like we're becoming more ordered. Okay, we have a solid and a gas. We have 2 different things on the reactant side. We just have 1 product on the product side. And it's a solid. We have no gas. So the fact that the gas goes away, it disappears, and you just have solid, definitely means you're becoming more ordered. But from the perspective of disorder, we're decreasing the amount of disorder. Okay, so that is true here. Delta S would be negative. Entropy is decreasing, becoming more ordered. All right, number 2, you have glucose, C6H12O6, it's solid. And on the product side, you have liquids and gases. This one I think is fairly easy. Sorry, they're all smushed together. I wish there was more space between them. But the fact that you have 1 reactant and you have 2 products, that in and of itself, you're becoming more disordered. And also the fact that you have only solids, and on the product side, you have liquids and gases, which are inherently more disordered. So definitely a positive delta S for many reasons on number 2. Number 3, we have 3 moles of a gas between our 2 reactants, ammonia gas and CO2 gas. Then on the product side, we have water and this other product, NH2, which is aqueous, so very similar to a liquid. And we know liquids are more ordered than gases. So the fact that we're going from all liquids to, all gases to liquids, delta S is negative here. We're becoming more ordered. So disorder is decreasing. Any questions on those? All right. 3 is not, this next question is not a math question. It's really more of a concept question. Kind of checking how well you understand how the delta S and the delta H fit together and what signs of delta G, what they mean. So it says, which combination of delta H and delta S for a reaction is not spontaneous at low temperatures and becomes spontaneous at higher temperatures? And if you were diligent in lecture, when we wrote in on the table, we made notes on the table for the delta G, delta H, delta S stuff. We pointed to one of those rows. We said, is favorable or spontaneous at high temperatures? And then we also labeled another. We said, is spontaneous at lower temperatures? That is exactly what this question is asking. Okay, which one is going to become spontaneous at high temperatures? We did kind of a thought experiment where we plugged in simple whole numbers on this one. We know that if you have a negative delta H and a positive delta S, that always gives you a negative delta G. Okay, so that's not the one we're talking about. And then vice versa, if you have a positive delta H and a negative delta S, these are the first 2 rows on the table. That always gives you a positive delta G. We're not asking about those. We're saying which one is delta G negative at one scenario or one condition and positive at another condition. So it's one of those bottom 2 where the signs on delta S or delta H are the same. And I'm seeing it in the chat now, they're saying when they're both positive. And that is absolutely right. When you have a positive delta H and a positive delta S, remember, because your equation is this, delta G equals delta H minus T delta S. So the larger this value is, the more negative this whole term becomes. And the more negative it becomes, the more likely you are to get a negative delta G. Okay. Which is congruent with spontaneous here. Any questions on that? So this is the condition at which you get are more likely to get a spontaneous reaction at high temperatures and a non-spontaneous reaction at low temperatures. Okay. This is a great question too. I think I put this on a quiz in previous semesters. The process of boiling a liquid has a what? So think about the process. Boiling a liquid. What happens? I would encourage you to write out a reaction for that. It doesn't matter. You can say it's substance A, okay, or substance X. We don't know what substance it is, and it doesn't matter. But in this reaction, you have some substance. We'll just call it A. And on the reactant side, it's a liquid. And as you boil it, that substance becomes a gas. So think about it. What are you doing with delta H and delta S here? Because it's asking you the sign on the enthalpy and the entropy. And we know enthalpy, that is your delta H. Entropy, that is your delta S. So delta S is actually the easiest one to define here. We're going from a liquid to a gas. You're becoming more disordered as you boil something. So yes, Jenna says delta S is positive. So we can already mark out the options here that says negative delta S. So negative entropy, that's not correct. Negative entropy, that's not correct. And we do have enough information. So that's not correct either. So it's either A or C. We need to figure out what delta H is. Jenna says it's positive. We just need to ask, we need to ask ourselves, are we absorbing heat overall or are we giving heat off overall? Is this an exothermic or an endothermic reaction? If you're boiling something, what are you doing to that substance?
Adding heat.
You're adding heat to it. And as a liquid, think about the level of intermolecular forces here. Exothermic, endothermic because you're heating it. Yeah, that totally is correct, Jenna. So let's explain this. Why is it endothermic? Liquid molecules, we know. I'm going to try to demonstrate without dropping my baby. We have liquid molecules and they're fluid. They can move past one another. Gas molecules are further apart. So with liquid molecules, we said there are some intermolecular interactions. Not as many as a solid, okay, but we have some molecules interacting more than in the gas phase. So to break all of those interactions apart, almost like they're bonds, but they're not the same as genuine bonds. But we still have to break them all apart so that we can expand the molecules into the gas phase. And that takes heat, that takes energy. So as we add heat, via a stove or a microwave or whatever, we are breaking apart any remaining intermolecular interactions that are keeping that substance in the liquid phase, and we're forcing it or pushing it into the gas phase. Okay, so it totally is an endothermic reaction because we are adding heat into it, and we're breaking apart bonds and moving it into the gas phase. So because it's endothermic, delta H is positive. So you want, which one is that? A, positive enthalpy and positive entropy change. This one's challenging, okay? You got to think about it in terms that we're not, we really haven't asked a style of question like that before. Any questions on that? All right. Okay, these obviously are problems right from your textbook. So we're kind of done with a little bit of, I didn't have a problem on here where you solve directly for delta G. I'll put one like that on the study guide. But we did several in lecture. We did several problems solving for delta G in lecture. So here we're going to do some equilibrium stuff, which I think is good because we did not get to practice a lot of that together. I had to do a video to give you that info, which I hated, but it's just the way it worked out. So for the reaction here, we have carbon monoxide plus oxygen making CO2. Says the equilibrium concentrations at a certain temperature are given here. And these mole per liter, we haven't got to chapter 9 yet, so I don't expect you to just recognize this. This is molarity, capital M. So instead of writing mole per liter every time, you can just write capital M. Write the equilibrium constant expression. Okay, what does that mean? Equilibrium constant. What is it asking you to do? It's saying write the equation for K. Okay. Remember, little refresher here, K equals what? It equals concentration of products raised to the power of their coefficient over concentration of reactants. Okay, raised to the power of their coefficient. And you're going to multiply those things. If you have more than one product, you would multiply all that on the top. If you have more than one reactant, you'll multiply all that on the bottom. So for this reaction, and remember here too, I mentioned this in the video, but you do not include things that are just solids or liquids. You can include things that are aqueous. You can include things in the equation that are gases. We don't include liquids and solids. So if something is a solid, you just ignore that. So K is going to be equal to Everything in this equation is a gas. So we'll put everything into our equation for K. So I'm just going to write concentration of CO2. It's not asking us to solve for anything, so we don't have to plug the numbers in just yet. We're just setting ourselves up to get the right equation. So CO2, we're going to square that. And on the bottom, we'll have our carbon monoxide and oxygen. They're both gases, so they both go. So concentration of CO squared times the concentration of oxygen. And that one's not squared or anything because the coefficient is just 1. So that's our equation for K. All right. Now, what is the value of K? Now we're going to plug everything in and solve. Get a number. So let's just rewrite the equation, but with our concentrations that are given to us in this row. So CO2, which goes on top, is the 0.11, and we're going to square that value. On bottom, we have CO is 0.025. We're going to square that. And we're going to multiply that by 0.11, which is 0.015. That is the value for oxygen. So make sure if you plug all this into your calculator all at once that you do the denominator in parentheses. The 0.025, squaring that, and the 0.015, put all that in parentheses. Don't let me know what you get for K. I'm a betting person. I think it's gonna be really small. Could be wrong though. I think it'll be small. Anybody got a value for K yet? 0.11 squared on top, and then divide that by 0.025 squared times 0.015. Okay. Abby said she got 8. Janelle, okay, wildly different answers here. And I realized too, actually, our denominator is going to be a very, very small number. When you divide by a very, very, very small number, you should get actually a very large number. So I haven't put this in a calculator. I would put all this in parentheses. Can anybody confirm or deny one of those answers? Jenna got something totally different. Okay, interesting. Could grab my calculator. I just don't. Let me grab it. It's literally right here. Ashlyn said I got what Jenna got. Okay. So 0.11, we're going to square that, divide it by 0.025 squared, come on, Bob, times 0.015. Yeah, I got 1,290.67. 1,290.67. Okay.
So I got that the first time, but I thought I did it wrong because you said it was gonna be a small number. So then I
Well,
redid it. Huh?
yeah, I was just looking at the denominator when I said that. Multiplying the 0.025 times the 0.015 gives you a very, very small number. But when you divide by a very small number, you get a big number. And then Abby says she accidentally squared O2 or concentration for oxygen. So recheck your numbers, but you should get 1,290.67. Yeah.
Okay.
Sorry to be misleading. All right. Second part of the question says that now you're going to solve for a concentration of one of these reactants or products. So this is what was giving everybody fits on the chapter 7 homework, because you had that N2O4 problem and you had to solve for concentration of reactant and product once you had a value for K. And that's exactly what you're going to do here. So you're going to take your value for K. Now you're just going to solve for a different piece of the puzzle. So you're going to use the same equation that we initially wrote out right here. And you're going to plug different numbers in and solve for whatever it tells you to solve for. So calculate the following. Calculate concentration of O2 at equilibrium when CO2 is 0.18 molar and concentration of carbon monoxide is 0.02 molar. So now we have K, and we can plug K in. But before I just plug numbers in, I actually want to rearrange my equation to solve for the thing that A and B are asking for. So I'm going to rearrange my equation to solve for O2. All right, so to do that, no, not feeling it, dude. Come on, one more problem. Let me get through one more. All right, so we're going to rearrange. So I'm going to multiply both sides of the equation by oxygen. Okay, because I have it, if you look, I have oxygen in the denominator down here, and I want to solve for it. I need to move it to the other side. So I'm going to copy this thing. And we know, all right, that equals K. So I'm going to multiply both sides by oxygen. I'm trying to get oxygen by itself. Now I'm almost there. Now I can divide both sides by K. And let's see what happens. What happened? Okay. K cancels on this side. Oxygen cancels on this side. And now I should have this. My new equation, I should have oxygen, O2, concentration of oxygen, which is what we're solving for, equals concentration of CO2 squared on bottom, carbon monoxide squared times K. So it's like oxygen and K just switch places. Then you just plug the numbers in and you get oxygen. So that looks like this. 0.18 squared on bottom, 0.02 squared, and then plug in K, 12, what was it up above? 1290.67. And K does not have units. Okay, y'all plug that into your calculator. I'm going to see if he'll lay down real quick. Be right back. We'll see what answer we got. And if you gotta go, thanks for joining us. At any point, y'all feel free to head out. We'll probably do a few more problems. We've been going for almost an hour. Jenna said she got 0.063. Abby got 0.063 as well. So looks like that is the common answer here. Again, make sure you do these things all in parentheses if you put it all into your calculator at one time. B would be the same thing. You're just solving this time for CO2. So what I'll do is I'll write out the equation you should get, but then you literally are just going to plug these numbers in to get K. So bye, Abby. So what should you get for your equation to solve for CO2? So we're going to take, again, the same equation. I'll kind of put it up here. And that all equals K. So now we're trying to solve for CO2. So to do that, I'm going to multiply this whole denominator. I got to move both of those terms. So cross multiply by carbon monoxide and oxygen. So what that looks like, you're going to say times concentration of carbon monoxide. Oh, that's not carbon monoxide. Squared, keep the square, and oxygen. And do that on both sides. Okay, so essentially you should have it looking like this. We cross multiplied by the whole entire denominator because we're just trying to get CO2 by itself. And then we got to undo this square here because we don't want concentration of CO2 squared, we just want CO2. So you just take the square root of both sides after that. So what you end up with is square root of CO squared times oxygen times K. That is equal to the concentration of CO2. And then you would just plug these values in for oxygen and carbon monoxide and this value in for K and take the square root of all of that. Any questions on that one? All right, I really want to get to Le Chatelier's principal problem, and that's what's next. So hopefully that helps clarify some things with equilibrium. Also, we didn't ever answer this part on B. Are reactants or products favored? Based on the value of K. K here, we got 1,290. So K is much, much greater than 1. I don't know if you guys remember. Towards the end, I'm going to scroll. Way down at the end, right here. This slide is the one I'm thinking of. When K is much, much bigger than 1, what is favored? Your reactants or your products? And if K is larger than 1, it says the reaction goes to completion. The forward reaction is favorable, so you're going to have more products than reactants. So products are favored. When K is big, products are favored. When K is less than 1, reactants are favored. So here we'd say products. Okay, any questions on that? All right. Next, we have a Le Chatelier's principal problem. So we have this reaction here, hydrogen gas and iodine gas is making, this is called hydroiodic acid, HI. And it has a delta H negative 2.2 kcal per mole. Now we're going to just change stuff and see how predict, based on Le Chatelier's principle, how will equilibrium concentration of HI change? So will the concentration of this particular product, So we're not saying it'll shift right or shift left here. We're saying would the concentration of HI increase or decrease based on how the equilibrium would shift. So it's a little bit different style of question than just what you were answering on your labs this week. So if we add some of a reactant, if we essentially increase the concentration of I2, what would happen to HI? Well, what does Le Chatelier's principle say? If we increase the concentration of a reactant, iodine here is a reactant, it says that we will use up some of that reactant. We're going to shift equilibrium towards products. Okay, when you increase the concentration of a reactant, equilibrium shifts towards the products. What that means is that H2 and I2 are going to react and they're going to give us more HI. So what will happen to the concentration of HI? That's what the question is asking. Will it increase or decrease? If we're making more of this, then we are going to increase the concentration of HI. So it will increase. Okay, B says what happens to the concentration of HI if we remove some of the other reactant hydrogen gas. So we're going to decrease the concentration of H2. And what is going to happen to equilibrium? When we add something, it shifts the opposite way. When we remove something, it shifts towards the thing we took away. So equilibrium in this case will do this. It will shift this way to replace some of the hydrogen we took away. So if equilibrium is shifting this way, what's happening to the concentration of HI? Well, we're using it up. We're going to make more of our reactants because we took some away. So the concentration of HI will go down. It'll decrease. And we said on 1, it would increase. Okay, C, what happens to concentration of our product here if we add a catalyst? What do y'all think? What does a catalyst do? Well, catalyst was up here on chapter 7. Before equilibrium, we said catalyst. It is a substance that increases here is no. Okay, it lowers the activation energy, but it does not shift, it doesn't cause a shift in equilibrium. It just causes the reaction to go faster. So this is a trick question and nothing happens. HI, our product, the concentration will stay the same. We might reach equilibrium faster, but we're not going to change the concentrations of anything at equilibrium. All right, the last one, D, says what happens when the temperature is increased. This has everything to do with this information up here, delta H. So this is where we need to know what this means. So if delta H is negative, is heat a reactant or a product? I'm going to rewrite the equation down here.
Product?
That's correct. And we'll just write in plus heat. So now it's very simple. Now we can just imagine that we're either increasing a product or decreasing. My goodness, I must have seasonal allergies. Delta S is negative. Do you mean delta H, Jenna? Delta S doesn't really, I don't think delta S will really affect anything right here, but delta H will. So if delta H is negative, we have heat as a product. If we are increasing the temperature, that is like we are increasing the concentration of heat. We're increasing a product. How is that going to cause equilibrium to shift? Towards the reactants or towards the products?
Left towards the reactants.
Correct. So if equilibrium, because of that, shifts left, what happens to the concentration of this guy? HI? Does it go up or down?
Decrease.
That's correct. We will decrease the concentration of HI when we shift towards reactants. All right. So this is the stuff I really wanted to get to from chapter 7 and at least kind of practice and review with you guys because we just didn't get to do a lot of that in lecture. So make sure you feel comfortable when I say writing out an equilibrium constant expression or write out the expression for K for any reaction. Make sure you feel comfortable with that and know that you don't include liquids or solids. If I had you solve for K and then make a comment about what your equilibrium conditions are, do you have more reactants or products? Do you favor the forward reaction or the reverse? And then equilibrium stuff. This is exactly the kind of style questions that you would have on the exam for Le Chatelier's principle. Sorry. Okay, that's really the end of chapter 7. Here's what we did not practice from chapter 7. We didn't do anything with reaction rates. Drawing out energy diagrams or drawing a reaction pathway with a catalyst or without a catalyst, labeling the activation energies or labeling a delta G. But we did all of that in lecture, okay? Here was 2 reaction pathways, one with a catalyst, which is the black one, one with a catalyst was blue, no catalyst was black. We did practice that in lectures. So if I had you draw out an energy diagram and label everything, hopefully you guys could do that just fine. If I ask you, what are 2 ways to increase the rate of a reaction or decrease the rate of a reaction based on what we talked about with rates and modifying temperature or concentrations of reactants or things like that, hopefully you could answer those pretty simply. But really, this gets into chapter 8 now, and this is gas law stuff. So what we'll do is, let me look at these really quick. Assume constant volume was a new temperature. The volume of this change wasn't. This is a lot of like Boyle's law, Charles' law, Gay-Lussac's law. I'm trying to find well, that was it. Was that it? These are the last 2 slides. Well, y'all just want to solve these real quick and then we'll be done? Might as well. We've been going for over an hour, but we literally just have these 3 problems left. Okay. All right, we're just going to knock these out. So this one is, I don't know what law it is yet. We'll figure out what law it is. It says a gas has a volume of 300 milliliters at 300 millimeters of mercury. So this right here is a volume. We'll call that V1. This right here is a pressure. That is units of pressure, millimeters of mercury. So that we're going to call that P1. That's the first pressure we're given. Then it says, what will the volume be if the pressure is changed to 500 millimeters of mercury? That's another unit of pressure. So this is what we're going to call P2. So this is Boyle's law, which was really all you have to know is the combined gas law. The combined gas law was the V1 P1 over T1 equals V2 P2 over T2. But here you're not given a temperature anywhere in the problem. If this is the case, you can assume temperature is constant. I will try to be more clear. I think I pulled this from the book. I would tell you, hey, assume temperature is constant. And if that's the case, remember, we just get rid of temperature and what we're left with is V1, P1. And it doesn't matter P1, V1 or V1, P1. It doesn't matter which one you're at first. Equals V2, P2. So it looks like we're solving for what? It says, what will the new volume be? Which is V2. We're solving for V2. That's what we want to find. So to do that, I'm just going to rearrange my equation and get V2 by itself. We'll just divide both sides by P2. And P2 goes away on this side. So our final equation before we just go plugging numbers in is V2 equals V1 P1 over P2. Now, the only other thing to check before you just throw all the numbers in and solve is that your units on pressure are both the same, and they are both millimeters of mercury. So we don't have any converting we have to do. If one was ATM and one was millimeters of mercury, then we'd have to convert one to the other. But they're both the same. So what we can do is plug in 300 milliliters, that's our V1, times 300 millimeters mercury divided by 500 millimeters mercury. And Jenna got 163.64 milliliters. So that equals 163.64 milliliters. That is V2. And this was boils. Probably on these problems, you see none of them come out and say, using Charles' law, solve for blah, blah, blah. So you kind of have to, because I want you to have a good understanding of the combined gas law. And when you know that, you just know. If you're not given a variable, or if you're told that something is held constant, then you just take that out of the equation and use what's left. Okay, next problem. A gas has a volume of 350 milliliters at 45 degrees Celsius. If the volume changes to 400 milliliters, what's the new temperature? Okay, so here we have nothing on pressure, no variables on pressure. So pressure must not even be important. We're going to take that out of the equation. What we're left with when we do that is V1 over T1 equals V2 over T2. Okay, so that's like we use this law up here, the combined gas law. We just this time took pressure out instead of temperature. Now it says report the new temperature in degrees Celsius. So we're solving for T2 because we're given our initial temperature. This is our initial, this is V1, and this is T1. And this right here is V2. And we want to solve for T2. But we cannot do this problem in Celsius. So we're going to have to convert T1 to Kelvin. Then we're going to have to solve for T2, convert it back to Celsius, and then we're done. So let's take our first temperature, which was 45 degrees Celsius. We add 273.15, 303, 318.15. Is that right? Is that your final answer, Jenna? Okay, we'll see if we get the same thing. So V1 is, we're gonna just plug everything in. Actually, before I just plug everything in, I like to rearrange my equation. So here is T2. So I wanna solve for T2. The problem is this is in the denominator. So do not just move V2 and think you're good. If you move V2 over, you have 1 over T2. So need to move T2, all right? One little trick when you solve these, I just literally flip the whole equation, okay? So what I'm gonna do, my first step is I'm just gonna flip it and say T1 over V1 equals T2 over V2. Now, if we multiply both sides by V2, V2 cancel on this side. What you end up with is V2 times T1, and on the bottom, we have V1. That equals T2. And I promise, if you would have done all the cross multiplying, everything else, all the other ways, you would end up with the same thing. So if you're trying to solve for, the note here is if you're trying to solve for something that is in the denominator, here T2 is on the bottom, just flip the whole equation, okay? Make sure you flip it, and get everything written correctly. And then it's usually much simpler to cross multiply or cross divide, rearrange the equation the way you need it. And now we can plug everything in. So our V1 goes on bottom now. So what is V2? V2 is 400 milliliters. So 400 milliliters, because we're doing V2 times T1, and we've got to use the Kelvin. And we're going to divide all of that by V1, which was 350 milliliters. And our units on V1 and V2 are the same. They're both milliliters. That's good. If not, we'd have to convert. Okay, 400 times 318.15 divided by 350. What do we get? And we're not done here. We have a temperature in Kelvin after that. We still have to convert it to Celsius. I got 363.6, and that's Kelvin. Now we just subtract off 273.15. And I got what Jenna got, 90.45 degrees Celsius. That is our new temperature. Y'all tired yet? Got one problem left. Almost there. Any questions on that one? This one was I believe this was Charles' law. Okay, last one. Here we go. The gases in hairspray can are at a temperature of 27 degrees Celsius and a pressure of 30 psi. Okay, and if it reaches 90 psi, the can will explode. To what temperature must the gases be raised for the can to explode? Assume constant volume. I'm disappointed because I thought this was an ideal gas law problem. Like I thought this was a PV equals nRT. I didn't look at it very closely. I really wanted to solve one like that, but I don't have anything else. We did, before we solve this problem, do y'all feel okay with PV equals nRT? We did one at the very end of lecture yesterday with the lung capacity of an average person. How many moles of air do you breathe in? If y'all feel good with that, that's exactly the style of ideal gas law problems we would have like on the exam. But I may put another problem. There's some practice problems on those, that back of the chapter textbook list on ideal gas law. If you have any questions, just shoot me an email on those. But I'm going to try to add a PV equals nRT problem for the Monday review. All right, this one is Gay-Lussac's law. Okay, so if we're at constant volume, what we do is we take the ideal gas law, V1, T1, P1 over T1 equals V2, P2 over T2. Assume constant volume, so we're going to just literally remove volume. And we are left with P1 over T1 equals P2 over T2. Now let's label the problem. This is our first temperature right here. So that's T1. This right here is our first pressure. So this is P1. And it says if the gases in the can reach a pressure of 90 psi, this is P2. So what temperature? Guess what we're doing? We're solving for T2. We don't have T2. So it's just like the problem right up above. We're going to flip the equation, get T2 on top. So if we do that, we'll have T1 over P1 equals T2 over P2. We're trying to solve for T2. So to get T2 by itself, I'm going to cross multiply, move the second pressure to the other side. That cancels right here. Now our equation is this. It is P2 times T, the first temperature, divided by the initial pressure is going to give us the final temperature, T2. So now we're just going to plug in. Where is my final pressure? 90 psi. That's P2. So 90 psi times, we got to convert to Kelvin. Our initial temperature is in Celsius, so 27 degrees Celsius plus 273.15, and you get 300, right? 0.15? Yep. Kelvin. So that's our initial temperature now. 300.15 Kelvin. Divide that by the initial pressure, which was the 30 psi. And we're good. We're safe to continue because we have the same units of pressure between our final and initial pressures. So 90 times 300.15 is Celsius. And divide that by 30. And we get 900.45 Kelvin. And the problem here does not say you have to revert it back to Celsius, so you would be fine to leave it in Kelvin. And that is T2. Okay, wow, we've been going for almost an hour and a half. That's a lot, but I commend you all for spending your Friday doing this. Hopefully it was helpful for the exam. If there's any questions, let me know. This recording will be posted, and Monday, people are going to do more of this. So y'all have a good weekend. I'll stick around if there's any questions, but if not, thanks for joining.